Consider the following riddle. A potter was moving in his bullock cart, for selling the clay pots he had made for the approaching summer, at a nearby town. On watching this, his brother, who didn't work as hard, started throwing stones at the clay pots out of jealousy. Many of the clay pots broke. The potter went to a nearest police station and requested the officer in charge to file compensation case for the broken clay pots against the violator. The officer asked the potter how many clay pots were broken. He gave the following response. If counted in sixes, 2 will remain. If counted in sevens, 1 will remain. If counted in 11s, 7 will remain. If counted in 13s, nothing will remain. My cart has a capacity for 300 clay pots. So, how many clay pots were broken? Let's solve the puzzle now. Assume the number of clay pots broken to be A. Then working backwards, we see that A is less than or equal to 300. If counted in sixes, 2 will remain, which translates to A equals 6 times P plus 2, for some natural number P. If counted in sevens, 1 will remain, which translates to A equals 7 times Q plus 1, for some natural number Q. If counted in 11s, 7 will remain. It translates to A equals 11 times W plus 7, for some natural number W. If counted in 13s, nothing will remain. It translates to A equals 13 times S plus 0, for some natural number S. In each of the conditions translated above as equations, we have a positive integer b which divides A and leaves a remainder r, that is smaller than b. In our example, b takes values 6, 7, 11 and 13, respectively, and r takes the values 2, 1, 7 and 0, respectively. The moment we write down such equations, we are using a theorem called Euclid's division lemma. Coming back to the riddle, do you have any idea how you will solve it from here? Yes. You must look for the multiples of 13 which satisfy all the conditions. By trial and error, using the concept of LCM, you will find the potter had 260 clay pots that were broken. Please pause the video and absorb what has been covered here, and then we can resume our learning. Now let us move ahead. Now, before we understand the Euclid's division lemma, that is also called interchangeably the Euclid's division algorithm, let us first understand the words algorithm and lemma. Algorithm is Latinized name of the 9th century Persian mathematician, Al-Khwarizmi, who is credited to have pioneered the field of algebra. He wrote a book called Kitab al-Algebra, which translates to Book of Algebra. The word algorithm can be defined as a procedure or set of steps to be followed in solving a problem. The word lemma can be defined as a proven theorem used as an argument or proof for another statement. Now that we know the meaning of these words, let us proceed to the topic. Please pause the video and absorb what has been covered here, and then we can resume our learning. Now let us move ahead. Euclid's division lemma is a theorem that states, given positive integers a and b, there exist whole numbers q and r satisfying the equation a equals b times q plus r, where r is greater than or equal to 0 and r is less than b. The application of this theorem is the Euclid's division algorithm, which is a long division procedure for computation of HCF, that is, the highest common factor of any two given positive integers. Please pause the video and absorb what has been covered here, and then we can resume our learning. Now let us move ahead. In order to find the HCF of two positive integers, we first identify the bigger of the two numbers as a and the smaller number as b in order to apply the algorithm. In step 1, using the theorem, we write an equation, a equal to b times q plus r, where r is greater or equal to 0 and r is less than b. Here, q and r are whole numbers. In step 2, if remainder r is equal to 0, then b is the HCF of a and b. If r is non-zero, apply the division lemma to b and r. We need to keep continuing this way till we have 0 remainder. The divisor at this last equation with 0 remainder is the HCF of a and b. This algorithm works because HCF of A and B is equal to HCF of B and R and so on. Please pause the video and absorb what has been covered here, and then we can resume our learning. Now let us move ahead. Let us see how the algorithm works through an example first. Suppose we need to find the HCF of the integers 497 and 42. We start with the larger integer, that is, 497. Then we use Euclid's lemma to get 497 equals to 42 times 11 plus 35. Now consider the divisor 42 and the remainder 35, and apply the division lemma to get 42 equals 35 times 1 plus 7. Now consider the divisor 35 and the remainder 7, and apply the division lemma to get 35 equals 7 times 5 plus 0. Notice that the remainder has become 0, and we cannot proceed any further. We can claim that the HCF of 497 and 42 is the divisor at this stage, that is, 7. You can even verify this by listing all the factors separately for 497 and 42, respectively. Please pause the video and absorb what has been covered here, and then we can resume our learning. Now let us move ahead.